Guardian is a combination of features, so we call it the Guardian Technology Platform. The basic idea of this is it's a family of features, and you sort of jump to the bottom. It's a family of features that we use to manage the NAND in a way that the NAND itself would not normally be managed, and the upshot of that management is that we can significantly extend the endurance of the parts. So we take a NAND that's, say, a 3000 PE cycle base capability component, and we can get it up to about 36,000 PE cycles worth of endurance. The benefit to that is obvious, and the benefit to SanDisk is obvious because we can use much less expensive NAND for, and compete against the guys who have no other option but to use the more expensive NAND. It also allows us to offer price breaks to customers that don't kill our margins. There's a number of different sections here. So flash characterization is a big part of Guardian. It's not simply a matter of you write some firmware and use the flash a different way. There's a fair amount of work that goes into the understanding how the flash is physically going to behave. It's not something that science is very good at predicting. So you have to sit down with the flash and you have to exercise it in a number of different ways and see how it behaves as a result of those stimuli, and then pick the ones that are going to give you the best endurance with the highest level of data integrity, obviously. So flash characterization is the first step of Guardian, and we do a tremendous amount of testing at the component level to understand how the flash is going to behave in order to pick the right path to get us to the high level of endurance. Endurance enhancement is what we realize out of that effort. It's really pretty much this simple. The features in the flash that control the analog section of the flash memory are called test modes. And the way a flash chip is manufactured, at the wafer level they characterize the flash and they choose a set of one-time program values for those test modes that are designed to guarantee the flash will meet its rated specification. So if it's a MLC class of flash with 3000 PE cycles, from one wafer to the next, the test mode settings will vary, but all of the parts that come out will achieve that minimum of 3000 PE cycles. But there's some implications there, and one of the biggest ones is that if you have 100% of the parts guaranteed to a minimum of 3000 PE cycles, the laws of physics demand that the larger part of the distribution is to the right, is outside of 3000. So you buy a drive that's rated for use with MLC flash at, it might be 3 drive writes per day is equivalent to roughly 3000 PE cycles at 28%. You run it to 3000 PE cycles, and there's still a lot of gas left in the tank, but there's no way for you to reliably take advantage of it because the SSD doesn't understand what that remaining margin is. So a big piece of the endurance enhancement is understanding, based on the behavior of the flash, what that area to the right of the 3000 PE cycle minimum looks like, so that we can take advantage of it to obviously get better endurance.
I'm sorry, this is in all your data center class products?
So this is in all of the Guardian class products. There's a drive circulating around that's Lightning. That's the Pliant technology. That does not take advantage of these features to the same extent. I mean, it's because SanDisk bought Pliant and then SanDisk bought Smart, and we have a future generation product that's going to blend the advantages of both product architectures together into a single one. So at the moment, it's got to say Guardian to be able to do this. Data integrity we talked about. We have a fairly strong ECC implementation. Can't go into a lot of details about it because, quite honestly, I don't understand it. But
okay.
Suffice it to say that the ECC features that we have are fairly unique and give us an advantage in terms of data integrity.
So is there digital signal processing also?
So not so much, no. Next product generation, I guess so the products we're working on, not the products we're releasing now, but the next generation after, those will use a different type of read channel technology called LDPC. Mm-hmm. And that is much more akin to digital signal processing, I think, than what we're doing now, which is, it's mostly in the digital domain.
Right.
We're just reading bits. It's not a lot different from the way a hard drive does it, we take advantage of some of the things we can do in flash that you couldn't do when you're writing to magnetic media, and that's why we get a better ECC than you might expect to see from a hard drive. And then frame I talked about before, and this is really an important feature, particularly because our implementation is designed so that page level failures, block level failures, there's 100% guaranteed recovery from those. But on some of our products, we actually provide coverage all the way up to the loss of a full die. So there's a slight reduction in the over-provisioning of the drive if a die fails, and that has maybe a negligible effect on the overall endurance of the device, and it may have a slight effect on the performance of the device, but I think people would prefer that over losing all of their data.
Yes.
Right.
So, and full die protection is something that is really only available on other products. It's only available on some competitor PCIe cards.
Right, and LSI does some page and block level.
LSI does some page, yes. So, I mean, there's no rocket science here, right? It's XOR, and it's just how you distribute the stripe that dictates what level of protection you get. You have to make trade-offs in performance and format efficiency as a result of the choices. So everybody does a slightly different implementation, but they're for the most part, they have to be the same because there's so many ways to do it. I also mentioned at the beginning of the discussion, one of the things that we think is unique to our products is we actually have a design criteria for performance change over the life of the drive. We do a fair amount of work to evaluate the drives to be able to show that the performance doesn't vary by more than 5% over the life of the drive. Power fail protection is pretty standard in any enterprise class drive now. You can get, a lot of client drives don't have power fail protection. The result of that is that they have much slower write performance. And they also can lose data in flight. They don't necessarily guarantee that you get 100% data integrity for data in flight. Power fail protection does do that. And those are the big highlights. So key components of the Guardian technology. We have to do a significant amount of characterization at the NAND device level in order to make this work. The fact that we have a memory group that actually invents NAND devices is a tremendous advantage. We dynamically and adaptively manage the flash test modes over the life of the drive, and that's really the key magic to it. There's a lot of complexity that goes into that rather simple statement, and the area to the right of 3000 is one example of a place we take advantage of that most drives can't. The other place that tends to resonate with people when I explain it is that the test modes that are set on the flash die are set to guarantee the die will meet its performance requirements at end of life, and the result of that is that it's settings that are designed and tuned for the flash when it's already worn out. And that has implications for when the flash is brand new. You're actually sort of writing it and erasing it harder when it's new than you need to ensure data integrity, to guarantee that you're writing it hard enough when it's end of life to guarantee data integrity. That stresses the flash and causes it to wear out a bit faster as well.
So are you doing things like dynamically adjusting the erase voltage?
Absolutely. Oh, we're doing all, if it's a knob available to us on the flash, the odds are very good that we're turning it, both for reads and write activity.
Yeah, unfortunately, I can't read the flash sheets.
Oh.
I've tried, and
well,
given the fact that I took my engineering classes in the 70s, some of the concepts.
These test modes are nothing you're going to find in a product specification. Anyways, they're really held near and dear.
Yeah, well, this is the why you want to buy your enterprise SSDs from somebody who has an intimate relationship with a foundry.
Correct. Absolutely. Absolutely. And I mean, we were developing this Guardian technology at SMART before SanDisk acquired us, and it was substantially more challenging to do.
Right. And yes.
Yep. Intelligent wear leveling is maybe a little bit worth talking about. Most SSDs work very hard at what they call uniform wear leveling. Basically, never rewrite any one location of the drive before you've written every other location at least once. To guarantee that you wear all of the flash out at the same pace. Because Guardian is actually dynamically assessing the capability of the individual flash in the drive, it does quite the opposite. It's almost non-uniform wear leveling, if you will. the flash that shows the highest capability is going to get written more frequently than the flash that shows the lower capability. Now, as the drive ages, those things are going to sort of seesaw around, and so it's going to change dynamically again as a function of the life of the drive. But you know, some of my customers, they want to know, you know, what are the PE cycles of the drive and what's the flash page with the most PE cycles? And they look for a large discrepancy there as an indication there's something wrong with the drive. On a Guardian-based drive, that's actually exactly what it's supposed to do. It's not an indication of a problem.
It just meant you found one really good page and you're going to keep writing to it.
Exactly. Exactly, and that's part of the you know, what we call the garbage collection magic as well, is that we reduce write amplification as a function of the locality of the workload to help take advantage of this kind of feature. And actually that's what that says. And we talked about powerful error correction already, so I'll skip that. So some terminology, aggregated flash management. This is a very important feature of Guardian as well. Guardian is really a statistical play. We take advantage of the knowledge that the flash is an undifferentiated population of flash is going to have a distribution of characteristics, and we can leverage that distribution if we understand it. We can leverage that distribution for endurance. We work very hard at minimizing write amplification, again, because anything that's going to unnecessarily degrade the lifetime of the drive is undesirable, because we're trying to squeeze every drop out of it we can. Advanced error detection code, so, you know, I mentioned this before, it's a 2-level BCH, which I sort of do know what that means. But the advantage of that is that it does give us a better correction span, because if you know, the span available to the BCH is redistributable throughout the sector, I guess, is maybe a approximate way of saying it.
So a given flash die's got some ECC space allocated.
Yep.
And you're exceeding that by using some of the data space as well?
So all flash has extra bytes, right? So when you get 128 gigabytes of flash, it's really quite a bit more than that.
Right.
We use that additional space for ECC, obviously, because the more ECC we have, the better. But it's not
if
just...
you were somewhat less reputable, you could use it for data and
make
sell a bigger drive. And
okay, yep, yes, we could. And the key, though, is it's how the BCH is distributed within the sector. It's not all at the end.
Right.
Right? And because of the way it's distributed within the sector, it actually can help us with the correction span depending upon where the defect is in the data.
Okay.
It extends the span.
And so does the fact that the flash varies statistically from its guaranteed minimums, is that taken into account in the smart reporting from the drive? So when I query the drive and I say, what percentage of your life is left, is that based on the experiential data that the controller gets through Guardian, or is that based on, well, this is 3,000 PE cycles and we've used 2,000 of them?
No, yes. So no, it's based, the drive understands what life it has left. It absolutely does.
Okay. And
yeah, it's not a fixed odometer count type of thing, right? Yes, absolutely. It knows how quickly it's wearing the flash, and the life reflects that wear rate.
Right.
And I've already talked about frame a bunch, so I won't talk about it again. So this slide maybe should have been a few slides earlier now that I'm looking at it, but I mentioned this before, that the flash die operating parameters, which they're called test modes, are tuned, selected at the time the flash is manufactured by the flash manufacturer.
Can you dive a little bit into what you mean by test modes? Is that program times, erase voltages, that kind of things?
It is. So flash, people tend to view flash as a digital device, and it really is.
No, it's not.
Right? So each flash cell stores an analog voltage, and in order to extract a digital value from that, there's a whole bunch of statistical processes that go on in the read chain, and then the flash die spits out ones and zeros based on that statistical processing. So the test modes are the parameters that set the various sections of the read channel and the write channel. They're also, it's voltages and it's timings. It's a whole slew of factors.
That's where I wanted. That's
I'm
that's
probably
the
not
level.
supposed to.
That's the level I needed you to go
But,
to.
I mean, erase time, erase voltage,
Right.
those kinds of things are easy to talk about because everybody's familiar with those terminologies.
Yeah.
But there are other factors associated with reads. To do a read, it's got to sample the flash cells and figure out
yeah.
where the mean is, and there's games you can play with thresholding on the reads in order to adjust those statistics. And it's basically all of these things that are controlled by Guardian. It's a very complicated implementation, it really is.
And those test modes can change over the life of the SSD, and
the behavior of the flash changes over the life of the flash.
Yeah.
And in a normal, like if you have a USB stick or compact flash card, you're using the same fixed settings across the entire life of that component.
Right.
So the settings have to be configured to guarantee operation at the end of the life.
Yeah.
Yeah.
In Guardian, we start out with this flash is brand new, and we don't have to erase it very hard to erase it. We don't have to write it very hard to write it, so we don't. And as the flash ages and you have to beat on it a bit harder to guarantee that you're getting the data to it, we increase those factors.
Right. Which you don't want to do at the beginning because using the hardware
Unnecessarily wearing it. Yeah.
Using the higher erase voltage wears out the insulating layers faster.
Correct. Yeah, I mean, it's like, if you put new tires on your car and then you sit in the driveway and you just spin the back tires, you're wearing them out unnecessarily.
Yeah, but I had fun.
And you're not going anywhere. It does make a lot of noise, too.
So how does the performance degradation guard band work here? I mean, it's not really Guardian per se. It's
Well, so
most SSDs have a precipitous drop after
and a lot of that has to do with error recovery.
error recovery
and ECC. So the things that change.
Doesn't seem like it should have to do with error recovery and ECC. It's something, the flash conditioning or something like that's going on or something like
Well,
that.
as the error rate increases, it's got to do more passes.
Well, because remember that if you look at let's use OCZ as an example because
Whatever you like.
I mean, their implementation just counts PE cycles.
Yeah.
Right? So they're using the flash devices the way that the flash supplier configured the devices
At
to be
3,000,
used.
it kills it out
Right,
and stuff like
right.
that.
But what they're doing is they're running them with the settings that they need at the end of the life. So they're already at the longer erase times and the longer program times.
You would think that would reduce their performance gap between beginning of life and end of life.
Except that the problem is that as the flash wears out, the ECC error rate goes up, and if you're not doing things to manage that ECC error rate, you're going into error recovery more. You have to do rereads.
Really, it is Guardian and its management of the NAND life cycle
That provides the benefit.
that provides the performance reduction in performance.
This chart, I struggled as to whether or not I wanted to include it because it's really rather specific.
Minimum bit error rate per EP lifetime count.
But yes, so it is rather. But it's not detailed enough for anybody to reverse engineer us, so I decided it was okay. But what this demonstrates is the Guardian's effect on the error rate. And there's a couple of key features. The really big one here is that you see that it's sort of, the curve starts to flatten as the flash gets older. So you don't need to do a very big, you don't need to get a very big gain or reduction in error rate towards the end of the life of the flash to make a pretty big difference in terms of the endurance or the performance. So what Guardian is really trying to do is it's trying to keep the error rate of the flash at a minimum across the entire working life of the flash. And doing that, because error rate and endurance are incestuously coupled, you have higher endurance if you manage to keep the error rate down. But you also maintain a better or a more consistent level of performance over the life of the device because you're keeping the error rate down. And it's a lot more complicated than that.
No doubt, yeah.
So I mean we've covered this one. I won't go through it again. We've covered this one, and we've covered this one. So we've touched on this, but Guardian is constantly adjusting over the life of the drive. The objective is to minimize the error rate across each phase of the life of the devices. The test modes are controlled to achieve that objective, and in so doing, we're actually minimizing the amount of wear that we do on the device, and that results in longer life of the device. And we talked on this, the harm done to the flash in the early phases is reduced as a result of the fact that we can manage the test modes dynamically. And all of these things combine to give us a device that has flash that lasts a lot longer than it would normally last if you just used it the way it came out of the box. And this chart you can't even see, so I'm probably not going to talk a lot about it, but it's kind of...
I think that's probably why.
Wow, maybe we could check
it's kind of motherhood and apple pie stuff, but basically what it says is that the synergy that you get with a technology like Guardian combined with a company that designs and manufactures its own flash is really a big deal.
Yeah.
All right, so we have this sort of life cycle where we bootstrapped ourselves in the first product generation with 24 nanometer NAND, and we learned a lot about how NAND behaved, and then we went on to the next one that you can't see here in the middle, which is 19 nanometer, and expected to see a lot of the same things we saw at 24, and were surprised to learn that there were some unique aspects associated with the geometry shrink that we needed to accommodate.
Yeah, there's the lovely fact that the smaller you make flash, the crappier it gets.
Yep. Yeah, well, the smaller the things get, right? So we have this sort of continuous feedback cycle now that Guardian is being implemented by a company that also manages the flash. We can tell the memory team what it is we've learned about the flash behavior. And it's interesting to note when we started this at SMART, it was Toshiba 24 nanometer NAND that we were using, and of course that's physically...
Well, that makes life a little easier.
Physically the same as SanDisk 24 nanometer NAND. But we did a whole bunch of characterization, and we went back to Toshiba with, can you help us understand what's going on here? And it was basically the first time they'd ever seen that data themselves. They were shocked to learn some of the things we were able to show them.
I think everybody in the room has gone back to a vendor and said, your product works this way, and the vendor said, really? We didn't know that.
True that.
So, and the leap from Toshiba to SanDisk NAND was relatively straightforward because we share the fab. The masks are the same. Now, Toshiba does their own post-processing and test mode selection versus SanDisk. We have different criteria we're optimizing on.
Right.
But the same physical devices made it a much easier leap than if we had started with somebody like Micron.
Right.
All right.
As a total aside, so the 15 nanometer stuff that came out, that was announced yesterday or today.
Yep.
Are you calling that 1Y or is that still 1X?
It's got to be X. I don't know.
No, it'd be 1Y or 1Z.
I thought it was 1Z. 1Z was in your press release for last week.
I think it was 1Z. I can double check.
When we get the tour of the memory lab, maybe there's somebody who could ask.
I bet the internet knows.
Yeah. Well, Google probably knows.
Google that for you.
Google probably knows. Yeah.
Google knows everything.
It does. It's spooky.
Sometimes I think Google's just a division of the NSA.
Or the NSA is a division.
Or the NSA. Yeah, I was going to say it's probably the other way around.
Yeah.
Who has the budget?
And I think that was the last slide. So that was the last slide, and look at that, 5 minutes to go.
Cool.
Wow.
All right.
1Z is the answer.
1Z.
1Z.
So what you guys need to do is get some baby clothing themed around that.
That's right. We should have pink and blue balloons.
Onesies.
Yeah,
Oh,
have
that's
1Z
horrible.
onesies.
Onesies. I get it.
Your speaking privileges are revoked for 5 minutes.
That was free.
So when you go to 12, so when it gets down to 12 or 11 nanometer,
that's the first time I've heard that.
we've run out of letters.
Yeah, and hopefully it'll be the last.
Yeah, maybe, but
Nah, that's actually pretty clever.